Good morning. Today we're going to talk about section 5.3 binomial probability distributions. Well, let me give you a little bit of a motivation for today's video lecture. Let's say I want to find the probability of two girls in three births. Well, we've done this many times in class, and of course we can find out that probability by listing the sample space. I won't bother to do it here. We've done it enough times. The probability of two girls in three births. Well, you've got 8 possible outcomes, allowing any child to be of any gender and in any order. And 3 of those outcomes have 2 girls and 1 boy in them, and thus the probability is 3/8. Alright, so largely this depends both on a little finesse and the ability to brute force write down the entire sample space. Well, as a motivation, suppose I wanted the probability of 50 girls in 100 births. If I wanted that probability, well, my number of outcomes, which would go in the denominator, is 2 to the 100th power. And a very huge number and much too cumbersome to write out the sample space. You'll be here forever and a day writing down the sample space explicitly. So what are we going to do? If we can't do it in a brute force first principle type of manner, well, I suggest to you that we need to develop a formula for what we call binomial probability distributions. Now notice the bi in binomial stands for 2 outcomes per trial. So this is really a binomial distribution. Let me define a binomial probability distribution a little more formally. A binomial probability distribution, well, really there's 4 criteria. It is a fixed number of trials. If you're looking for the probability of 2 girls in 3 births, well, of course, then you have 3 trials. Number 2, the trials are all independent. In other words, the outcome of any one trial doesn't affect the probability of any other outcome in any other trial. 3, there's 2 outcomes per trial. Labeled somewhat arbitrarily success or failure. Okay? Alright, so we can see 2 girls and 3 births. Well, that's a binomial experiment so far anyway. You've got 3 trials and 2 outcomes per trial, namely a boy or a girl. And the 4th criteria here is the probability of success or failure remains constant across all trials. Right here, in all trials. Alright, so these 4 criteria define a binomial probability distribution. A fixed number of trials, the trials are independent, there's 2 outcomes per trial, and the probabilities are constant throughout all trials. Alright, let's talk about some notation here before we develop a formula. I'm going to let S equal the event of success, and cap F equals the event of a failure. The probability of success in any one trial we will label lowercase letter p. The probability of failure in any one trial is lowercase letter q. Well, of course, if there's 2 outcomes per trial, then q equals 1 minus p. Lowercase n will denote our number of trials. In the experiment, lowercase x will be the number of successes in n trials that we are looking for. And P of x, really the goal of it all, is the probability of getting x successes in n trials. Okay? Alright, we're ready to write down our binomial probability formula. Our binomial probability looks like this. Well, the probability of x successes in n trials. Well, again, I'm going to denote that with this shorthand. It's P of x, or probability of x, equals n combine x, or n choose x, times p to the x power times q to the n minus x power. Okay? Note, this component here represents x successes, so raise p to the x power, and you're looking for the component of x successes. Well, if you've got x successes, you've got n minus x failures, and this component represents the probability of n minus x failures. And this factor here, n choose x or n combine x, it's really the number of ways to arrange x successes and n minus x failures. Okay? So really this product here, p to the x times q to the n minus x, it's the probability of x successes and n minus x failures in any particular order and this factor here, this n choose x, in fact is the number of ways to arrange x successes and n minus x failures. And of course our calculator can work all this out for us. N choose x, that's a command under the stat menu. These are simple algebraic expressions which I can plug in, but in fact I don't need to, because this formula is programmed into our TI 8384 calculator. Right, so let me write this down. You're going to need your calculator today, so if you don't have it yet, I want you to get it out and get it ready. This formula is programmed in the TI 83 or 84 series calculator. Okay? And we will, for the most part, be relying on the TI 8384 and its advanced power to grind out probabilities of this type. Okay? Alright, let's do an example of this, of using this formula. Well, let me start out with a simple example. Find the probability of 2 boys in 3 births. Well, we already know what that is, right? Assuming, of course, boys or girls are equally likely in any birth. Well, we've got 3 births. I could interpret that as 3 trials, 2 outcomes per trial, namely boy, girl. The probabilities of boy or girl are constant in each trial, and of course all the trials are independent. That's kind of implied in the scenario here. So I claim this is a binomial experiment. Or a binomial probability distribution with 3 trials. Right? The number, if I let a boy be a success here, remember I'm looking for 2 boys, so if I'm looking for 2 successes, I'll let x equal 2. My probability of success in any one trial is going to be 0.5, and hence my probability of failure, q is always 1 minus p, that's also 0.5. So armed with these parameters, I could grind things out with my binomial probability formula, but instead we're going to use in our calculator as a command called binom PDF. And we'll give you the syntax here. Right, the syntax runs so. You plug in little n first, then p, then x. Right, remember, n is the number of trials. Little p is the probability of success in any one trial. And x is our number of successes that you're looking for. Okay, so there's my binom PDF operator. Again, for this example, n equals 3, little p equals 0.5, and of course x equals 2. Alright, so all I need to do is call up that binom PDF command on my calculator, and it saves me much of the handwritten drudgery if I wanted to apply the formula from first principles. Alright, to find this command, it's under the distribution menu. If you look on your calculator, above the vars button on your keyboard, there should be a distr, D-I-S-T-R, or a distribution menu. And that's where I'm going to access this formula. Alright, so on the calculator, hit your second gold button. Turn mine on here. Second gold button, and then the vars button to access the distribution menu. So second vars to get to the distribution menu. And if you scroll down on my calculator, it's function address 0 on that vars or distr submenu. You can scroll down, or just in my calculator it's function address 0 to call up the binomial PDF command. Alright, so second vars, highlight binom PDF, right, and the command should be called up into your home screen. Alright, once you're there, you plug in these needed values here. Recall for this particular example, n equals 3. We've got 3 trials. The probability of boy is 0.5 in any trial, and I'm looking for 2 successes in any one trial. Alright, so once you call up the command binom PDF, enter in these values and hit enter, and you should get a calculator return of 0.375, which of course equals 3/8, which of course we know is the correct answer. Alright, so again, the calculator in its wonderful power has this somewhat nasty formula already pre-programmed in, and we're going to take full advantage of it. Alright, let's do another example, maybe a little harder one. Well, maybe it's not so hard now. Let's write down, let's see, I'll say find the probability of 50 boys in 100 births. As again, as we mentioned earlier in the lecture, if you've got 100 births, that means you've got 2 to the 100th power possible outcomes. So many, you literally could probably not write down all the possible outcomes in a lifetime. Alright, so, but with our binomial probability distribution formula, maybe with a little finesse, we can grind this out without too much trouble. Now, we've got 100 trials. again, assuming boy or girl are equally likely in any trial, the probability of a boy, and we're going to call a boy a success here because we're looking for 50 successes, the probability of boy is then 0.5. Again, with that assumption, the number of successes we're looking for is 50. Alright, so really this is kind of a breeze now. The probability of 50 boys in 100 births is, well, again, I'll go to second level on my calculator, hit the vars button to get to the distribution menu, and call up Binomial PDF. By the way, PDF stands for probability density function, and the binom stands for, of course, binomial. Right. So again, the syntax is n is, well, the n is the number of trials. So we've got 100 trials. The probability of success in any one trial, of course, is 0.5, and we're looking for 50 successes here. Alright, so call up this command, enter in these parameters as indicated, and punch it out, and I get a final answer of 0.079. So the probability of 50 boys in 100 births is in fact 0.079. Okay. I want to do an example in the book now. This is example 2 on page 213. Let me turn there myself and read it. Give me a minute here. Here we go. Twitter. Something about Twitter. All right. Given that there is a 0.85 probability that a randomly selected adult knows what Twitter is, use the binomial probability to find the probability of getting exactly 3 adults who know what Twitter is when 5 adults are randomly selected. Alright, we're going to use binomial PDF formula on our calculator again. We're talking about knowing Twitter, and we're asking 5 adults, so we've got 5 trials here. Do you know about Twitter? And they say, the book says explicitly that the probability of any one person knowing Twitter is 0.85. So the number, let's see, the little p, the probability of success, we're going to call knowing Twitter a success here, is 0.85. Alright, the number of successes we're looking for, well, let me see here. Find the probability of getting exactly 3 adults. So we're looking for 3 successes in these 5 trials. That's an 8 there, okay? Alright, so again, we'll go to Binomial PDF. Hit your second button on your calculator, your vars button to get to the distribution submenu. Call up Binomial PDF. You'll have to scroll down. Again, in my calculator, it's function address 0. Your function address may vary depending on which calculator model you have. In any case, find Binomial PDF, highlight it, and hit enter. Call this command up into your home screen and enter in N and P and X for this example. And I punch this out on my calculator and I get 0.138. Right. Now the text works this out by hand from first principles, using that binomial probability formula. I see no reason why we can't use the binom PDF command on our calculators exclusively. Alright, I want to talk about some homework type problems here. Let's look at number 30 in our text. This is on, hang on a minute, what page is it on? Page 220. Alright. Let me read the problem. Live TV, number 30. Based on a Comcast survey, there is a 0.8 probability that a randomly selected adult will watch primetime TV live instead of online or on DVR, etc. Assume that 7 adults are randomly selected. Find the indicated probability, and we got A, B, C, and D. And I think we can grind all these out without too much trouble. Alright, we've got 7 adults being randomly selected. So I've got 7 trials in this experiment. Alright, we want, let's see, the probability that they will be watching prime time live instead of other options, that's given to us as 0.8. Right, so my little p is going to be 0.8. And number of successes that we're looking for, well, that's going to vary between each part of this problem. So let's say number A, letter A, we want the probability that exactly 2 of the selected adults watch primetime TV live. So 2 successes in 7 trials. So go to your binomial PDF command. Hang on. Slip there. Binom PDF. Number of trials is 7. Probability of success in any one trial is 0.8, and we're looking for 2 successes in those 7 trials. If we punch this out, we'll get an answer of 0.0043. Alright, so I'll box this and call part A done. Let's look at part B. Still number 30. Find the probability that exactly 1 of the selected adults watches primetime TV live. Well, this given information is the same except for my number of successes. I want 1 now. Alright, well, I'll call up binom PDF command, and still got 7 trials. Still the probability of success in 1 trial is 0.8. Well, instead of 2 successes, you want exactly 1 success. Let me check it. Yes, exactly 1 success. Alright, now if I punch this out, well, I get something in scientific notation. Let's talk about that in a minute. For a minute. 3.584 E minus 4. That's what my calculator returns. This is Texas Instruments syntax for scientific notation, and what this means is 3.584 times 10 to the minus 4th power. Okay, this E, this cap E between the numbers means scientific notation, and here is the equivalent, right? Well, we should all know a little bit about scientific notation. All this means is you'll move the decimal place 4 places to the left if you want to get to a decimal representation. All right, so 1, 2, 3, 4, there it is. There would be my equivalent answer in non-scientific notation. Either of these answers are acceptable. They're both the same, equivalent anyway. And we're ready to go on to part C. Find the probability that fewer than 3 of the selected adults watch prime time TV live. Fewer than 3. Well, let's see. Okay, we're going for part C down here. The probability that X fewer than 3 means less than or equal to 3. No, it's less than or equal to 2, right? Fewer than 3 means 0 or 1 or 2. Right? Notice the 3 case is not included here because 3 is not less than 3. Alright, so I don't really want the probability that X is less than or equal to 2. Right? Well, I can say this is the probability that X is 0 plus the probability that X is 1 plus the probability that X is 2. Right? Taking the 0 case, the 1 case, and the 2 case and adding them up individually according to our addition rule. Right? Now, you may notice the 0 case and the 1 case we already have from parts A and B. Let's see. No, I'm sorry, the 1 and 2. Let me say that again. The 1 case and the 2 case we've got from parts A and B already. So 1 success, right? Sorry. The 1 success was in part B. Right? So that's 0.0003584. A little mixed up there. Plus the 2 case, that's from part A, is it not? So all we really need to do is add on the probability of the 0 case, in other words, the probability of 0 successes in 7 trials. And I'll type that out here. You'll need binom PDF 7, comma 0.8, comma 0. So if I punch this out on my calculator. Now, I'm going to need more room here. I have to switch to a new screen, unfortunately. Give me a second. All right. The probability of 0 successes in 7 trials is 1.28 times e to the minus 5th power times 10 to the minus 5th power, plus, of course, the 1 case, and, of course, the 2 case that I had previously computed. And, of course, 1.28 times 10 to the minus 5th power, that's equivalent to 0.0000128 plus 0.0003584 plus 0.0043. Alright, if I add those all up, I get 0.00467. So that's my answer to part C. The probability of fewer than 3 is then 0.00467. Alright, let's look at part D. If we randomly select 7 adults, is 2 unusually low for those who watch primetime TV live? Let's grind this out. Is 2 unusual? Well, we have to find out the probability that x is 2. Well, again, we've already found that out. The probability that x is 2, we found out that's part A, right, was 0.0043. Now, what are the guidelines our author gives for unusual? Well, if a probability is less than 0.05, our author has the convention of calling that an unusual event. So I'll say since the probability of x equals 2 is less than 0.05, 0.05 represents a 1 in 20 chance, kind of a 1 in 20 milestone. We'll see again. We'll say it is unusual. Seems somewhat arbitrary perhaps, but as we'll see later in the semester, maybe not as arbitrary as you might think. Right? An event is unusual if the probability is less than 0.05. That's the convention our author has established earlier. Alright, so part D, our answer to part D would be yes, 2 is an unusually low number. Okay? Alright, that's number 30. Let's see, I want to do one more. Number 37 in our homework list. And where's number 37? Well, that's on page 221 in our text. And let me read it. CBS television televised a recent Super Bowl football game between the New Orleans Saints and the Indianapolis Colts. The game received a rating of 45, indicating that among all U.S. households, 45% were tuned to the game, based on Nielsen data. An advertiser wants to obtain a second opinion by conducting its own survey, and a pilot survey begins with 12 randomly selected households. Right away I know my number of trials is going to be 12. I asked 12 people, did you watch the Super Bowl? Okay? Alright, part A, we want the probability that none of the households is tuned to the game. Right, let me write part A here. Well, the probability that any one house watches the game is 0.45. That's told to us explicitly in the problem. And for part A, we want the probability of no successes. So here we're calling watching the Super Bowl a success, and the probability of success in any one of these 12 households is then 0.45. Okay? Alright, so of course then I want to grind out my Binomial PDF operator. We've got 12 trials. The probability of success in any trial is 0.45, and here in part A we're looking for 0 successes. Alright, so my calculator returns 7.66e minus 4. Again, that's scientific notation, which is equivalent to 0.000766 in decimal fashion, right? So I would just box that. that is my probability, and a pretty low probability, as you might expect. Super Bowl is a pretty popular game, and out of 12, you might think the probability that nobody watches it is pretty low. Let's look at part B. Find the probability that at least one household is tuned to the Saints-Colts game. All right. We want at least one. What does at least one mean? It means, well, I want the probability that X is greater than equal to 1. Now, I could do this the long way, or I could do this the short way. You've got 12 households you're interested in. I could grind out this formula 12 times for the 1 case, the 2 case, the 3 case, all the way up to the 12th case. I don't want to grind out this formula 12 times, especially since I think I can find a better way. Right? Well, remember, the probability that X is at least 1 is 1 minus the probability of none. Right? Really, I have 13 cases from 0 up to 12, and I can find out the probability that X is greater than or equal to 1 by taking 1 and subtracting the probability that X equals 0. You may recall that in any probability distribution, all the probabilities have to add up to a 1, right? So the easiest way to grind this out is to take 1 and subtract the 0 case to get at least 1, or the probability of at least 1, and that I've already got, right? But this probability that X is 0, well, hang on a minute. No, we don't already have it. I'm going to have to grind it out, so let me do 1 minus, I'm going to do binom PDF. Right, we need to grind out the 0 case, right? So I've got 12 trials, a 0.45 probability of success in each trial, and looking for 0 successes. Right? So that's 1 minus 0.000766, and I get 0.999234. And again, you would think that the probability that at least one of these 12 households watches the Super Bowl is probably pretty high. Alright, so that's part B. Part C. Part C, let me read it. Find the probability that at most one household is tuned to the Saints-Colts game. Well, I want the probability of at most one success. Now, what does at most one mean? Well, at most means 1 or less, so I claim this is the probability that X equals 0 plus the probability that X equals 1. And one of these numbers we already have from part A, right? The probability of 0 successes is, of course, 0.000766. And the probability of 1 success, well, I can grind that out with, let me get it all in one screen here. Binomial PDF. Let's see if I can slide over. I've got 12 trials. 0.45 probability of success in each trial, and for this piece I'm looking for 1 success. Alright, if I punch this out, and you can type in your calculator just like this, you don't need to find this probability intermediately. If you like, and that's what I like to do, punch it all in one line of code, let the calculator do as much work as you can, and I get 0.00829. Let's look at part D, last part for the day. If at most one, let's see, if we randomly select, if at most one household is tuned to the game, does it appear that the 45 share value is wrong? Why or why not? Well, what they're getting at here, if at most one is watching the game, that happens with this very low probability. And if this probability is very low, you might think there's something wrong with the assumption of a 45% share of the TV audience. Let me write that out. Say, if at most one is indeed, most 1 in 12 is indeed watching the game in a group of 12, that probability is equal to 0.00829, a very low probability, which is certainly much less than 0.05. Right? Which would be a very unusual event, right? So this suggests, if this event is indeed happening, that perhaps, not for sure, but perhaps the assumption of a 45% share of the TV audience is wrong. Okay? But again, we don't know for sure. It just suggests this. Alright, we'll call it a day. It's about 36-minute point. This concludes section 5.3, video lecture, binomial probability distribution.